FRM Part 1, Book 2, starting the Quants book, Quantitative Analysis. And the very first topic of Book 2 is Fundamentals of Probability. A nice, gentle way to take us into quantitative analysis. But just before we jump in, just by way of intro a little bit, guys, just how does quants differ in 2020 from how it was in the past? Okay, essentially not a whole batch of difference. Okay, then what? For example, if you're looking at this FRM course the second time, perhaps, not a whole batch of difference. Okay, than what it was in previous years before the changes were made. Obviously, as you know, 2020 was a big change year for them. They rehashed the whole syllabus. But at the end of the day, guys, always remember that quants is quants is quants. You can't change probabilities. Okay, you can't change random variables. Okay, it all is what it is, and they remain very static. Okay, maybe that's where the word statistics comes from. I'm not sure. Don't think so though. Okay, but it all remains very much the same, guys. Not a whole batch of change. Okay, what has happened, and obviously which is a little bit confusing, okay, is that when you look at the syllabus, you don't recognize any of the topics. Okay, you know, for example, we start to look, as we go through them, they start to talk about common univariate random variables, and you think, well, where was that last time? What is that even? Okay, you know, if you look through, there's no specific sections on hypothesis test. Well, there's one on hypothesis testing, but they're not using too much of the same terminology, too much of the same stuff that we saw in the past. Okay, so that's one of the changes. As I say, nothing too crazy. It's really just a case of changing names around, changing places where things once were. I mean, if you have a look at what we're going to be doing in this particular topic, topic 12, fundamentals of probability. Okay, everybody's favorite. We'll talk about learning objective 12G, Bayes and Bayes theorem. Now, Bayes theorem in the past, last year, had its own whole topic in and of itself. So what they've done is they've cut away a little bit on Bayes and just plugged it into the probability theory, which is its correct place, by the way. It's not a bad place to put it. So everything's nicely reorganized for us. No cause for alarm. They haven't put in anything too crazy. Okay, they've left that, of course, for FRM Part 2. No, just kidding. That's going to be fun as well. But just the topics have changed quite a bit. And again, on the back end, right on the back end, guys, there was a whole batch of funny stuff in previous years. They've cleaned up that a little bit. Some of it wasn't really that relevant, or shouldn't have really been in there, in my humble opinion. But so they've cleaned up quite a bit of that, so made that look a little bit neater on the back end. Okay, in terms of what they are going to ask and what they're not going to ask, it does seem to be a fairly evenly weighted book. And what I mean by that, unlike for book 1, where we saw, okay, that there was massive weighting, for example, for topic 5, which was CAPM, and topic 9, which was financial disasters. Here, much less so. There seems to be nicely weighted across the entire book, and of course that makes sense though, because quants is quite, you know, it builds upon each other. You know, we'll go from linear, simple regression to multiple regression to hypothesis. It all tends to build quite nicely. But the approach that we're going to be taking, particularly for book 2, is we're going to go nice and slowly. Okay, and we're going to be working through examples as we go through to try and make it as practical as we can. I don't want book 2 to become everybody's bugbear. Well, we'll score higher elsewhere because we can't score too much on book 2. Remember, book 2 leads on to FRM Part 2 and leads on to other things that you're going to be doing either in practice or other designations that you look at, anything like that. And interesting, I'm doing it with the Kaya guys at the moment, and they do a lot of quants, particularly in Kaya level 1. Okay, so you're never going to be free from it, so we're going to get it right. That's going to be our approach. Get in, work hard, and really just kill book number 2. Okay. Guys, let us jump straight in and make some headway over here. And as we say that, it looks like it's a massive topic, like 40 or something pages. I don't know exactly how long it is, okay? But it does look like it's a massive, massive topic. But don't stress, because what I've done is I've just been copied this directly from what we had in the previous notes on probability from last year. And why we've done that is because the first if you look at our edge note over here, the first, I don't know how many pages, all the way up to page 26, where we actually start topic 12, fundamentals of probability, okay, is really just calculator work and time value of money. So the entire next 26 pages, and don't turn off the recording now, because don't worry, I won't be doing it with you. Okay, it's not specifically examined anywhere, by the way. You know, for example, once we get to book 3 and book 4, VRM, valuations and risk models, okay, and 3, financial markets and products. Yes, you need to know how to do time value of money calcs, etc., but it's never examined as a specific section per se, and obviously we'll handle each bit of calculator work as we need to and as we get to those particular sections. So what I want to do is just, you know, if you have a look at it very briefly, guys, we talk about interest rates, we talk about compounding, we move from there, from all the different compounding. If I just switch across some pages over here, effective annual rate, the EAR. Yes, it's a fantastically important calculation, the EAR, the effective annual rate. But again, we're going to see that when we get to it in its correct place, of course. When we look at, particularly in book 3, when we look at some of those rates, things like on bonds and things like that. Okay, so I'm not going to be doing this with you guys. Obviously, if your time value of money is not where it needs to be, please do take a peek at these particular notes. Have a read through. It's very, very simply done. And what I've done is I've given you all the workings, both manual, okay, and both with the use of a calculator. And obviously the calculator that I love to use, and that most of the service providers are recommending, is obviously the Texas. Okay, having said that, guys, we do have some of the workings on the the HP as well, if anybody needs. So if you're trying to do a calculation, and remember at FRM level, you can use the other HP calculator, which you can't use for CFA and Kaya, which is the 10B. Okay, so if you need help on that, you can just reach out and scream. I've given you a few calculations. We do present values, we do future values. There's time value of money on page 8. Okay, but you guys are all familiar with this. There's nothing new I could really show you over here. And again, as I say, we're going to see these in the correct places as we go forward. So what I'm going to do now, okay, is I'm just going to turn pages. Okay, this is the intro section, and again, not specifically covered. If you have a look at your learning objectives for topic 12, it's not there, of course. Okay, so it's not specifically even addressed as part of your learning objectives. There's annuities, future value, present value, future perpetuities, all the calculations. And guys, again, they are vital calculations. They're very important stuff, but not specifically related to here. Albeit that a lot of the service providers do put it in here, it's not part of the learning objectives, but important nonetheless. So we have put it in for you, and there we go. There's a little bit on timelines there on page 20, the different calculations, cash flows. Really, by the time, if you went through this particularly in great detail, up until here where we see our first learning objective, 12A, you would have a wonderful working knowledge and understanding of time value of money and use of your calculator. So guys, depending on the time that you've got available, it might be very worthwhile to go through this particular intro in great detail. Let's start the actual reading itself, guys. Probabilities. Okay, and we're going to go slowly, guys. Okay, it's the only way I know how, and obviously quants can get a little bit tricky, but also what I want to do by the time we reach the end of book 2 is to have a bit of a sense of quants and not say, oh, topic 12 was probabilities. Okay, well then what was topic 13? Topic 13 was random variables, and then 16 and 17 are sample moments, for example, and hypothesis testing is 17, and they all work on their own. No, I want us to look at them as one complete section called quants and statistics, and how everything talks to each other. There's a link between everything, guys. Okay, and the more we can see that link, the more the understanding behind quants will come, and the more basic and easy it's going to become for us. Okay, we talk about sort of describe an event and an event space. Okay, okay, and we start off with probability, guys, and probability is really Okay, first of all, it's a fundamental section of statistics, very, very important. Okay, but that we knew. And it's the chance of something occurring. Okay, and remember, guys, this is not the first time you've seen probability. And you know how I know that? Because I did an example with you as part of the book one final wrap-up. We did 10 questions together, and one of those was a CAPM question, and in order to get to the expected earnings, okay, I had to times the earnings under various situations of the economy times the probabilities of those happening. It's that probability that we saw in that question, I don't know what it was, I think it was question 5 or question 6, is exactly the same probability as here. Nothing's changed. It's the same good old probability, the chance of something happening. Okay, we move down to some of the definitions which are important. A random experiment, and how do you know that it's random? It's an experiment, and it's random because we don't know the result in advance. Okay, tossing a coin, rolling a dice, playing the lottery, anything like that will be called a random experiment. Outcome is the result of the random experiment. Event, okay, an event is a group of one or more possible outcomes. Okay, so for example, if what I'm trying to define is all the even numbers, and what we learned about probabilities, which makes them, you know, sometimes confuses people a little bit, is we're just going to give them a name. So if I say over here A, what's A? And I can define A. I can define A as anything that I want. Here I've defined it as all the even numbers. In such a case, what is my event? My event is called A. What is A? A is all the even numbers when I roll the dice, and therefore A could only equal to 2 or 4 or 6. Okay, so we will go and name and give classifications to our events. The event space, that's the space within which the events work, all the possible outcomes that could occur in a random experiment. So say, for example, okay, I'm looking at rolling a dice, okay, and when I roll the dice, I can get a 1, a 2, a 3, a 4, a 5, or a 6. So first of all, is that a random experiment? Yes, it is, because before I roll the dice, okay, unless of course you're playing with my sons, that they know the outcome beforehand somehow, but most people don't know the outcome beforehand when they're playing rolling a dice. Okay, so it's a random experiment. Okay, and the event, let's say for example I define the event as all the numbers on the dice. What's my event space? It'll be a 1, a 2, a 3, a 4, 5, and a 6. It'll go from 1 through till 6. Okay, good. Okay, good. We move along a little bit. Let's go. Okay, let's have a quick look at an example. Okay, here's an example of a probability. Okay, I'm on top of page 27. Suppose we know that a certain share price has a 40% chance of going up, 35% chance of dropping, and 25% chance of remaining the same. We can define them. Remember, these are all events. What are my events? The event is event A. I've called it A, but if we don't give them names just yet, before we give them their names, A, B, and C, what are the events? Well, the event 1 is the share price goes up. Event 2 is the share price goes down or drops. And event 3 is it stays the same. Now what we can do is we can give them names. We can just call them what we like. I've chosen A, B, and C. We could have gone X, Y, and Z. We could have gone anything that we like. Okay, and you're going to see just in terms of labeling of probabilities, I call it P. Very fancy. Okay, P stands for probability. So now if I say PA, what does PA mean? PA means the probability of A happening. And what's A? Well, I defined A up here. And that is the share price going up. And what's the probability of it going up? Well, we spoke over here. And guys, just try your best to denote stuff in terms of how they like it. It'll just make it easier as you go forward in your studies to work in how they work. The probability of A, share price going up, 40%, B, 35%, and C, 25%. And obviously, we move down from there to the very next very important concept, the properties of probabilities. Number 1 is that they always lie between 0 and 1. Inclusive. Okay, there we go. All of these numbers, the probabilities, the 3 probabilities lie between 0 and 1, and they sum to 1 or 100%. Okay, and then of course that's also here. These sum to 100% or to 1, whatever you want to call it. Same thing. Okay, good. Okay, good. Okay, those are the first two. We see another property over here. It's not often put into the notes, but FRM does like it, so I'm going to give you three. Normally talk about the two properties of probability. Here we're going to talk about three. If the events are mutually exclusive, okay, then we can just sum them together. Okay, and I'm not going to stress about that right now. I want you, mutually exclusive means, okay, only one of them can happen. So if I talk back to my share price example over here, those are mutually exclusive. The share price can only, it can't go up and down. It can't be A and B. Okay, and why can't it? Because it can't go up and down at the same moment. It can go up one time and then the next time it can do something else. But when I'm looking at it, what's the chances tomorrow of it going up? 40%. And to go down, 35. And to stay the same, 25. They sum to 1. Okay, they sit between 0 and 1. Okay, and they are mutually exclusive. So if the events are mutually exclusive, we can just sum them together. Okay, and by the time we come out of probabilities, there's really as complicated as the section is. It's not an easy section, guys, probabilities, but as complicated as the section is, okay, there's really only about 5 or 6 different permutations. Okay, which we will need to know all of them. Okay, good. Okay, good. So mutually exclusive, guys, it can only be one or the other. So when you're rolling a dice, the outcomes, okay, are mutually exclusive. Why? Because it can only be a 1, a 2, a 3, a 4, a 5, or a 6. When you roll a dice, it can't be a 1 and a 6. Or it can't be a 1 and a 2. It can only be one or the other. In other words, the events, my 6 events over here are all mutually exclusive. And if we just had to, just for fun, if I had to say to you, what is the probability? And I can label it. Let's say, for example, I want to call it up here. I'm going to say A is equal to, that I get a 1. Okay, so now if I say to you, what's the probability of, let's try and keep it a little bit the same color. What's the probability of A? In other words, what's the probability of getting a 1 when I roll a dice? Well, it's equal to, guys, 1 over 6. Whatever that happens to be, I think it's 0.16. Okay. And the probability, if I had to call getting, if I had to label B as getting a 2, the probability of B is also, by the way, 0.16. And so we go, why? Because they are mutually exclusive events. Each one will fall between 0 and 1, and they will all, of course, sum to 1. Okay. We spoke a little bit earlier, guys, about random variables. Okay. In other words, okay. A random variable is very similar to a random experiment. Random experiment we spoke about before, that I don't know the outcome of the experiment before. Okay, we don't talk about a random variable. Okay, and what's interesting, guys, very important we get this concept right now. Random variable, by the way, is topic 13. Okay, so we're seeing a bit of a definition for it up front. Okay, the variable, okay, is the thing that takes on the values. Okay, for example, the random variable in our previous case, okay, is the share price. Okay, and it acquires probabilities that sum all the way up to 1. Okay, and we're going to see much more about random variables as we go forward. Okay, very important, of course, guys, the outcome of the random variable is not known in advance. Okay, and why is it not known in advance? If we're going to define the random variable, okay, like we're saying over here, guys, so important, the random variable is the share price. If we're going to call the random variable the share price, of course we don't know what it's going to be up front, and of course we don't. Why? Because it could go up, it could go down, and it could stay the same. Okay, good. Point dot number 2, okay, the probabilities, okay, will tell us, and that's obviously what the probabilities are there for, okay, how likely each event is going to occur. Okay, and as we can see over here, if I take you back right up to the front, okay, the probability of it going up, okay, which we defined as A, okay, is 0.4, so there's a much higher chance of it going up than there is of it going down and of it staying the same. Okay, but of course, guys, any of the three events are possible. Okay, because they all have some probability attached to them. Okay, good. Okay, if we talk about top of page 28, okay, another example of a random variable is a coin toss. Okay, and remember, coin toss can only be one of two things. It could be a head or a tail. Okay, so the what is the random variable? The random variable is the result of the toss. Okay, same thing with the share price. It's the outcome of the share price. Okay, good. If the coin is fair, which you hope that it is, the chance of each outcome, okay, is 1 out of 2 or half or 0.5. And again, that fits in very nicely to the definitions of probabilities. In other words, that the probability sum, each individual probability falls between 0 and 1, and they sum to 1. Okay, we move on. Okay, random variables, okay, which is what we're talking about over here, very important, guys. Again, we're going through a lot of definitions tonight. Can be discrete or continuous. Discrete means it can be a specific number, or continuous means any single number within that particular range. Okay, good. Okay, we talk about a probability distribution. Okay, and all that it is, guys, a probability distribution, okay, specifies all the probabilities or the possible outcomes of a random variable. Okay, that's all. Okay, so what are all the possible outcomes in this particular distribution? Okay, if we go back to my example and we say, I'm going to toss the coin 3 times. Okay, what now? I want to get the probability distribution. Now, the probability distribution, okay, means that I'm going to have for every as I say, every time that I roll the die, toss the coin, okay, it can be a head or a tail. Okay, so if I'm, and it's very important that we look up here that we're going to toss the coin 3 times. Okay, so and obviously the more times I toss it, the more possible outcomes I've got, of course. Okay, but if I'm only going to toss it 3 times, what are my outcomes? Well, they could. We see over here that there's 8 possible outcomes. It could be every time I flip it, I could get a tail. Every time I flip it, I could get a head. I could get a tail, then a head. Then I could get a tail, head, tail, head, tail, 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 head, 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 tail, head, and head, head, tail. So those are the possible outcomes. Okay. Okay. Of these, only one, which is if it goes tail, 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 has 0 heads occurring. 3, okay, have 1 head occurring. 3 have 2 heads, and 1 has 3 heads. Okay, so if you look over here, when I'm looking at my probability distribution, and remember, guys, don't overly complicate stuff. A distribution just is the possible outcomes. That's all. Okay. So if we look over here, guys, if X is the number of heads, the number of times that I get heads, okay, is when I spin the coin, X is equal to 0, 1, 2, or 3. And why is it that? And remember, guys, all I've done over here, so we're going back to what we did before. Nothing's changed. If X is the number of heads, okay, and I've given it a name now. That's all. I've called X number of heads. Okay, I could have also called it H. H is equal to, but I've called it X. Why did I call it X? No idea. Okay, that's just the name that it was given. Okay, and now we say we look over here, and what is the chances? Well, there's a chance there could be 0 heads. There's a chance it could only be 1 head, or 2, or 3. What are the probabilities of it happening? What's the probability? I'm just going to do the first one with you. What's the probability of there being only 1 heads? Sorry, let's do the first one of 0 heads. Well, what would that be if there's 0 heads? Then what must the outcome have been every single time? Tail, tail, tail. And that would be 0 heads. And what's the chance of that happening? Only 1 out of the 8 chances. So now we go over here and we say, what's the probability of there being 0 heads? 1 out of 8. What's the probability of there being 1 head only? And guys, you can just, I'm going to clean up here a little, and you just can't count. What's the probability of there only being 1 head? Let's go. Well, there's 1 head. It's 1. There's only 1 head there. There's only 1 head there. Over here, no, here there's 2 heads, 2 heads, 2 heads, and here there's 3 heads. You guys comfortable? So what's the probability of there being 1 head? 3 out of the 8. 2 heads, 3 out of the 8, and 1. And what's the probability of there being 3 heads? 1 out of the 8. And that is a nice, easy example, guys, because you could physically count them. Okay. And by the way, guys, you've just covered probability distributions. Okay, and what the probability distributions does for us is it records the probabilities for the possible outcomes of what? Of the random variable. What's the random variable? I'm taking you back up again, guys. Very, very important. In our case, the random variable in a toss of a coin is the result of the toss. In other words, heads or tails. When we talk about the random variable in the share example, that's the outcome of the share price, which is either going to be what, guys? Up, down, or stay the same. Okay. Good. We talk about 2 kinds of random variables. The one random variable, guys, is what we call the discrete random variable, which can be counted, which is what we did over here, guys. This is a discrete random. I can count. I can physically count, and we did that, didn't we? We said how many heads in the very first one over there? None. And here, 1, and there 1, and there 1, 2, 2, 2, and we physically could count them. Okay, that's what we call a discrete random variable. A continuous random variable, okay, is I cannot count them. They can't be counted. They can be measured, though. Okay, good. And we're going to see, for example, okay, what would then constitute to see a discrete random variable is quite simple. And those are most of the ones that we deal with. Okay. But a continuous, in other words, it's continuous. The number of outcomes are just too vary. So, for example, if I say, okay, guys, 10 people entered the lift, what's the weight of the people in the lift? Okay, and we add them all up. And now, what is their weight? Well, their weight is the 10 people. If you put them all together, is what, 750 kilos and 0.1 point this point that grams. You can't. There's too many. The possible outcomes are too many to count. Okay, but we can measure them. Okay, it is and that's the key difference between continuous random variable is measurable, discrete can in fact be counted. Okay, good. Okay, over our page. Okay. Top of page 29. If the random variable, and we're just continuing a little bit over here with continuous variables, was the weight of a randomly chosen person in kilograms, okay, then theoretically the random variable, it's not, I don't know if these notes are being generous at all, could take on the value from 0 to 300 kilos. That's one big guy, okay. And it's not possible to list all the possible outcomes. Why not? Because you could say, well, I found a guy, and I'm trying to guess the probability if I pick a random person off the street, what his weight will be. Well, what will his weight be? His weight, well, let's say no man can be less than, I don't know, 40 kilos. So the first guy could be 40, the second guy could be 40.001 kilos, and then 40.002. It's too numerous to list all the possible outcomes all the way then up to, of course, 300 kilos. Okay, so we call this a continuous as opposed to a discrete variable. I can measure it. I can take the guy, I can measure him and say, oh, this guy measures whatever, but we can't count each and every single possible outcome. Okay, good. Okay. And we move down. The next 2 concepts are vitally important, guys: exhaustive and mutually exclusive. Mutually exclusive means only one event can happen. Okay. In other words, the events are completely separate from another. So, and look at the words I'm using. I'm using the same words all the time. Okay. Events. What are events? So if I roll a dice, my events are what? 1, 2, 3, 4, 5, and 6. And we could name these. What's the probability of getting a 1? We could call that an A. Remember, we could just give names to them just to try and make them a little bit easier to use. Okay, so the events, okay, mutually exclusive means, okay, that, for example, when I roll a dice, the outcomes are mutually exclusive. And why are they mutually exclusive? Because no outcomes can be the same. I can't get a 1 and a 2 at the same time. I can't get a 4 and 5 at the same time. I can only get one of them. That's mutually exclusive. Okay, exhaustive is exactly that. Okay, I exhaust all the possible outcomes. So again, rolling a dice would be both mutually exclusive, the outcomes, and the outcomes are exhaustive as well. Why? Because I can count them. It's going to be a 1, it's going to be a 2, it's going to be a 3, a 4, a 5, or a 6. It's not going to be a 27. It's not going to be a 562. Okay, they are exhaustive. There's only 6 that can be. If I flip a dice, flip a coin, it's exhaustive. Why? Because it can only be a head or a tail. It's also, when I flip a coin, mutually exclusive. Why? Because it can only either be a head or a tail. Okay, it can't be both. Okay, so those two definitions are very important, as we'll see as we go forward. Okay. Learning objective 12b, describe independent events and mutually exclusive event. Well, we've dealt quite a bit with mutually exclusive already. We're going to take a look at independent events. Okay, and the difference between independent events and conditionally independent events. And it's very important, guys, as we move forward now, is not to get bogged down by the definitions, but rather to understand what the definitions are saying to us. Okay, let's start off with independent events. Okay, two events are independent. Okay, independent, and it's easy to remember. Independent means that neither one influences the other. You know, I'll read you the formal definition. Two events are independent if the occurrence of the one does not in any way affect the occurrence of the other. Okay, and I keep threatening to change this example because I don't love it. I don't think it's technically correct, though. In practice, of course, in real life. If C, the price of an insurance share C goes up, and D is the price of insurance share D goes up, then C and D are dependent events. Okay, because why? The market as a whole might be bullish, or the insurance sector alone might be having a good day. Although the increase in share price C might not affect D at all, there's a good chance that they're going to move in the same direction. Okay, if A, a person in Europe driving a red car, and B, a person in Australia driving a white car, then very clearly, if I'm trying to work out what's the probability of a man in Europe, a person in Europe driving a red car, and a person in Australia driving a white car, these events are clearly independent. In other words, there is no bearing; they have no bearing on each other. Okay, as opposed to over here where there might be some link between them, but we're not completely sure. Obviously, guys, I'm not going to, that's why I don't love that example, the first one. I prefer this example over here. In terms of an independent event, they have no bearing on each other. Okay, good. And we start off over here, we throw a formula at you straight away, okay, and we're going to go through it in much greater detail as we go through, and as I said to you, if you remember correctly earlier on, that there's only about 5, maybe 6 different permutations for probabilities, and here we start. Okay, and we start off and we say PAB, okay, the probability of A and B, okay, is equal to, and we're going to go through this again as we go forward, guys. We just had to throw it in over here because we were talking about independent events. Okay, is the probability of A times the probability of B. They are completely separate from one another. Okay, and of course you can say the probability of AB is equal to probability of B times the probability of A. Okay, and when the events are independent, they're not linked to each other, it's just a times. It's a times. Let's have a look over here as I move down. Remember, it's just a times. Why is it just a times? Because they are not linked to each other. They are not dependent on each other. I don't have to say, if this happens, then that happens. They are completely independent of each other. So I just multiply their probabilities of occurring. Let's have a look over here. In a bullish market, 3 shares chosen from different sectors, so we've been quite specific over here, there are different sectors of the market, have probabilities of 0.6, 0.5 and 0.8 of their share prices rising on a particular day. I'm going to call the shares K, L and M. Okay, good. If we make the assumption that the prices of shares on successive days are independent of each other, okay, then we're going to, and again, don't make a lot of this example, guys. I'm not sure if it is correct. I mean, if we could even say such a thing, that the share prices on successive days are not linked. Perhaps they are linked. Okay, so don't read too much into this. This is obviously, when we look at this example, that's what I'm making as my assumption. Okay, then we can carry out the following calculations. Okay, let's say, for example, and I want to know what's the probability. Always remember, we put a P first. The probability of share K rising on 2 consecutive days. And now, if we're going to say that the probability of rising on consecutive days are independent events, okay, then it's purely going to be 0.6 is the probability of an up move on day 1. What's the chance of it going up on day 2? Well, it's not linked to day 1 at all, so I don't have to consider the relationship from day 1 to day 2, and I just go 0.6 times 0.6. In other words, there's a 36 or 0.36 probability that share price K being an rising, which is an independent event, will rise on 2 consecutive days. And 3 consecutive days, well, I'll add another 0.6 in front, and so we go. As you can see, then of course the probability drops considerably as we go forward, as I add on the number of days that I want it to go up. But very important to remember, guys, because I'm assuming that the probability of the stock going up, okay, on or down is not linked from day to day. In other words, it's an independent event, therefore it's a times. Okay, we move on. Okay, what's the probability of shares L and M both rising on one day? Again, I times them by each other. Why? Because it's independent. They're independent of each other. They're not linked to each other. So it's the probability of U happening and the probability of U happening. I can just times them out. And of course, if we know that the events are independent, it makes our calculations so much easier. Okay. Good. I'm not going to spend much more time over there. Okay. Good. Okay. Nothing more that we can add over there. Okay, I'll move to the middle of page 31. There's just a few. We carry on with those examples, nothing too detailed over there. We move to a slightly different and so important in probabilities that you read the question very carefully. Because now it says, what's the probability that at least one of the 2 events will occur? Now, at least, okay, one of the 2. In other words, A occurring or B. This is the OR rule. Okay, so we've seen the independence rule. We saw that. Now we come into another rule. It's A or B. Okay. And now let's have a look at I'm going to throw the formula at you, and then we're going to start to look at an example or 2. The OR rule, the probability of at least one of 2 events occurring is, look how we denote it. It's the probability that stands for the P of A or B. Okay, and now look what I've got. Okay, it's the probability of A happening. Okay, plus the probability of B. And why do I just sum them together? Why am I allowed just to sum them together? Because I don't care which one it is. I just want one of them to happen. So I don't care if it's A. I don't care if it's B. So sum them together, and as long as one of them happens, I'm happy. But look what I'm doing now. So the big question is, if I'm saying to you I want it to be the probability of A or the probability of B happening, why don't I just say it? Okay, then let's just define this as being then the probability of A happening plus the probability of B, and I don't care which one. But yet I don't stop there. Okay, I go minus PAB, minus PAB. And what is minus PAB? Okay, minus PAB is the probability of both. Now we need to talk about this in a little bit more detail. And why do I do that? Because remember, guys, what I'm begging for in this particular section is complete understanding. Even if it takes us all night, we work slowly. Okay, good. Okay. Then I'm going to say something over here. So this is, and we have to fully understand both. This is number one. This is formula number two. Look at formula number two. Formula number two now does do what I want it to do. It says it's a probability of A or B. It's the OR rule is equal to the probability of A plus the probability of B, and there's nothing more after that, like there was in number one. Why is there nothing more now? And the reason there's nothing more over here because the events are mutually exclusive. In other words, it's rolling a dice now. Okay. Now, if it's rolling a dice, okay, the events are mutually exclusive. It can be a 1, a 2, a 3, a 4, 5, or a 6. Both events can't happen. Okay. So, assuming that we wanted to, let's say, for example, I'm going to work on number 2 first. We'll get to the other one in a second. Let's say, for example, I want to look at rolling a dice, and I'm going to say, I'm going to call the probability of A getting a 1 and the probability of B getting a 2. That's all that I want to work with for now. Yes, I know there could be a C, D, E, and F, which is the rest of the numbers on the dice. I choose not to work with those right now. Okay, now, the probability of getting a 1 on a dice is equal to, we worked out before, 0.16, or 1 out of 6. Probability of getting a 2 is also 0.16, or 1 out of 6. That's my probabilities for those. Now, if I had to say to you, what then is the probability of getting an A or a B? In other words, a 1 or a 2. It's just going to be 0.16 plus 0.16, which is equal to 0.33. Okay, you can see a little bit of a joint probability, A or B. Okay, why didn't I minus anything behind there like I did in example 1, the probability of them both happening? Because you can't get a 1 and a 2 together, can you? Because the events are what? Mutually exclusive. Okay, so 2 is mutually exclusive. But then what I do, take you back, I go PA, put that formula there. And remember again, guys, there are only 5 or 6 different permutations that we need to work with. When then would I work with number 1? I would work with number 1 when they are not mutually exclusive. In other words, one event, A or B, can happen simultaneously. Okay, we need to talk about that. Let's talk about that. Let's do an example. Okay. We look at an example of playing cards. Okay, the probability of A and B. A is going to be getting an ace. Okay, and B is getting a spade. Okay. And what would I say? Okay, if I now have to say to you guys, what's the probability of A or B? In other words, what's the probability of getting an ace or a spade? And what do we know about cards? We know, okay, let me just clean up a little bit. Well, let's go down over here. What do we know about cards? Okay, let's break them down. There are 4, I think they call them suites. There's hearts, diamonds. I don't know how to draw spades. No idea. I'm not a cards player. I'm just going to call it spades. And I'm trying to think what the last one is. Hearts. I need some card players. Okay. Hearts, diamonds, spades, and I'm not sure. We're going to call him other. I do apologize about my card knowledge. Okay. What I do know is that there's 13 cards there, 13, 13, and 13, giving you a total of 52 cards. Okay, and now if I say to you, what's the probability of getting Remember, we're working, let's just look over here again, apologies. We're working with ace or spades. Now, if I want to say it's an ace, okay, or a spade, let me just break it down a little bit further. Within each of these four suites, okay, within each of the four suites, there's 13 cards. What are the 13 cards? An ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, 9, 10, Jack, Queen, and King. There's the 13 for all of those. Now what I'm asking you in this particular question, okay, I'm asking you, okay, I want an ace, or how many aces are there? Well, there's an ace there, there's an ace there, there's an ace there, there's an ace there. There's 4 aces in the whole pack, and I want to know what's my probability of it being an ace or a spade. Now, the probability of it being an ace, there's 4 aces out of 52. How many spades are there? There's 13 spades out of 52. So if now I to say to you, what's the probability of ace or a spade? You would say, well, the probability of an ace, there's 4 aces in the pack out of 52, plus there's 13 spades out of 52. And then you would say, well, then I'm done. But that wouldn't be the right answer here. And the right answer over here, there's the 1 out of 4. That's the probability of it being an ace. There's the 1 out of 13, the probability sorry, that's the probability of an ace, 1 out of 13, and there of a spade, 1 out of 4. Remember, 1 out of 4 is exactly the same thing as saying 13 out of 52, which is what we used down here. And 4 out of 52 is the same thing as what we got over here, guys, which is 1 out of 13. But look what they're doing on the end over here. They're going minus 1 out of 52. This is number 1 again, guys. They're saying the probability of an ace or is probability of A, an ace, plus the probability of a spade, less the probability of it being both. What? Both. Which is 1 out of 52, because remember, okay, let's clean up. When I look over here, remember, okay, here's all my spades. What's the probability of it being a spade? We said 13 out of 52. Happy. What's the probability of it being an ace? There's 4 aces. So aces, so spades, 13 out of 52. Aces is equal to 4 out of 52. But remember, look at this now. Something crazy over here. There's one card that's the same. Remember, there is look at this. There is a ace of spades. So within this particular thing, I've double counted for one of them, so I've got to go minus one card that is the same, 1 out of 52, which is, and what card is that exact card we know? That's the ace of spades, which I've accounted for him twice. I account for him here in the spades section, and I account for him in the aces as well, but there is an ace of spades as well. So when something is not mutually exclusive, in other words, it can occur twice, in other words, the ace of spades, that same card is the same for both of my A and of my B, then I've got to go for formula number 1, and I've got to subtract. You see that over there. So it's the probability of A plus the probability of B less the probability of both. In number 2, they are not mutually, in number 2, sorry, that we talk about mutually exclusive, they are mutually exclusive, and in such case, then I have to, I don't have to worry about taking it off, because it can only be one or the other. It cannot be, both of them cannot be the same card or the same event. Okay, good. And that's the whole explanation behind all of this, guys, when we talk about the OR rule. We show it very nicely over here on top of page 32 that there's an overlap. There's your aces, okay, and there's your spades. But there's one card that's what? That sits in between them, and that's the ace of spades. He's got to go. Okay, and that we can see it over there. And the card that relates to both, then we call the probability of A and B. Okay, good. Now, just in case, okay, we're trying to cover all of our bases over here. Sometimes they like to ask this in terms of different kinds of notations. Okay, I've shown you the one notation over there. Okay, let me show you the other one now. Okay, it looks like this. We call it the intersection operator. Okay, and if we go like this, A, B, okay, with the intersection operator, what does that mean? The set of outcomes that occur in both A and B. Okay, when I look at like this, when I use the union operator and I go A, I shouldn't have done it like a U, it's more of a much nicer looking U, A, U, B. Okay, this is the set of outcomes that occur in either, not this is the either one. Okay, so this one is the or, and that is the and. Okay, and that's it. I wish I could make it more complicated than that, but this one over here, you can see it again over here. I'll keep the colors consistent. PA, the probability of A and B happening. I use the intersection operator, and the probability the or A or B happening, I use the union or the joining operator. That's it. Okay, let's have a quick look at an example over here. Okay, assume we're looking at the following two events when rolling two dice. Okay, that the sum of the two dice is greater or equal to 9. That the sum of the two dice when I roll them is an odd number. Okay, we're going to call event 1A. And what's the probability of A? And what is A? A is that it's greater than or equal to 9. And probability B is the sum of the two dice is equal to an odd number. Okay, so let's start over here. A, okay, and I'm going to use my intersection operator. Okay, the set of outcomes that occur in both A and B. Okay, in other words, what numbers, okay, would there be in both? Now the probability of A, okay, said the sum of the dice is greater or equal to 9. So then what could it be? What could, if I had to look at my all the possible events for A, the event space, it could be a 9, a 10, 11, or 12. What could the probabilities of B be? I want all the numbers of the dice when I roll two dice. Remember, two dice gives me a total of 12, and that the sum of the two is equal to an odd number. Okay, so remember, it can't be 1 because I'm rolling two dice, so I've got to start with a 3, a 5, a 7, a 9, 11, and that's it. Okay. Now, if I'm going to say to you, is everyone happy with that example? Okay. And what I've done over there is I've said the probability of each of those the different event spaces. Okay. Now I'm going to say let's talk about the probability of A. Now I'm using intersection. Intersection is and. What's the chance of them both happening? What would both A and B happening? Okay. Okay. And what are the only two numbers that are repeated in both of those? The probability of both happening, a 9, you see that over there, and an 11. That's it. Okay. Good. That's it. Okay. And that's the intersection or the and operator. Okay, take you back over there. Okay, that's the and. And a silly way to remember, if it helps you, great. If it doesn't, well, is it looks a bit like an end, an and, the next one. Almost looks like an and. Okay, if that helps you, great. The intersection one is the and. And means both. Okay. And how does this help with when we talk about things like independence? Okay. For example, again, if they're independent of each other, they have no bearing on the occurrence of each other. In other words, there's no link between how the different events might occur. Okay. Okay. So let's move on. We can use the following rules for independence. Okay, the probability of A given B is the probability of A, and the probability of B given A is equal to the probability of B. And why is that? Because they are independent of each other. So the probability of A happening given that, and that's, we're seeing something new over here, the straight line means given that B happens is exactly the same thing as the probability of A happening. And why is that? Because B is not linked to A at all. So who cares about what happens to B? Because what happens to B is not going to impact A at all. So the probability of A happening is the probability of A happening. Given that B happens, who cares? B is not impacting here at all. We move down. What's the probability of B happening given that A happens as well? Who cares about A? It's just equal to the probability of B, because A is independent of B. They are not linked. So this is almost like the second term over here. The given that is a bit of a red herring, and that doesn't mean anything to us when I'm talking about two independent events. So guys, we can just see as we move through here just how important independence is, because it's just so vital that we understand, okay, when we talk about independence, okay, that the other term becomes quite irrelevant in a sense to us, because what's the probability of A happening given that B and C and D happen? Well, who cares about B, C, and D? Because they're completely independent of A. So the probability of A happening given that something else happens is exactly the same thing as probability of A happening in and of itself. Okay, we move forward. Okay. And I'm not going to spend too much more time over there. And again, when they are independent, and we've seen this before, what is the probability of A and B happening? Okay, when they are independent of each other? That's the times rule. Remember that one? We saw that already. That's the times rule. What's the probability of let's say, for example, getting the share price of 2 shares going up? Well, assuming that the shares are independent of each other, well, you would times the two up probabilities by each other. It's the times rule. There's nothing else that comes in here. These are when the events are independent of each other. Okay, and we'll do more examples as we go, but vitally important that we understand these completely. Okay. Let us move along. Okay, a probability matrix, okay, summarizes the joint probabilities of independent events. And all that a probability matrix does, guys, is it just summarizes the calculations have already been done for you via the table. Okay, so we got a table over here, and let's say, for example, I am looking for the joint probability. Joint is and of a good market and stock prices moving up. So what's the probability? So for market being good is there, stock prices moving up is there, and I meet in the middle over there. It's almost like reading off a table. There's a 35% joint chance of the market being good and that stock prices move up at the same time. Okay, what's the probability of there being a bad market and stock prices moving up, advancing? Only 5. And that makes sense, of course, doesn't it, guys? Because in a bad market, stocks are not likely to advance. In a good market, there's a much greater chance of them advancing. So when you look at a probability matrix, it just allows you to read off the table in a much easier fashion. Okay, good. Those were all unconditional probabilities. Okay, unconditional. Okay, they are not linked. They're not dependent. They're independent of each other. Unconditional probabilities. We move to a new concept over here called conditional. And conditional means it's conditional upon another event. We look over here. What's the probability of and remember this, A and B occurring, okay, And now I put over here an interesting one. Given that C occurs. Okay, so in other words, there's a link now. Okay, A and B happening. A and B are not just going to happen in and of themselves. There's something else that needs to that they depend upon, that they are conditional upon, and that happens to be event number C, and that's called conditional. We don't see too much more of that over here, guys, but that's called your conditional independence, and obviously that is going to be something we'll focus on a little bit later on. But for the most part, the work that we work with, it's independent events, okay, and we have a brief look. Just remember, guys, it's not the key focus over here. We have a very brief look, guys, at conditional independence. Okay, for example, A and B might be independent of each other, but it's conditioned based on another event that we might need to look at. We're going to put a little bit of a pin in this one. We'll come back to it, but don't let that be the key focus of what we've seen thus far.